Welcome back. We're going to do one more example. We're going to find center of mass as well as moments of inertia about the coordinate axes. And we're also going to find that polar moment of inertia. So we are dealing with a thin triangular plate bounded by three lines, y equals x, y equals negative x, and y equals 1. And in this situation, our delta, our density is not a constant. Our density is variable. So it's 3x squared plus 1 kilograms per meter squared. Now, as we work through this problem, I'm really going to focus on the setup. And once I have the integral set up, you guys should be very confident in computing these integrals at this point. So I'm just going to give you the answer, if that's okay. I feel like the computations in this problem are really easy, and I just wanted to show you this just to make sure we know how to set everything up, especially when we have a density that is not constant. Whenever we're working on these problems, we always want to think about our region, and our region is bounded by the lines y equals negative x, which looks like this, and y equals positive x, and y equals 1. So this is our region. Now, when we think about setting this up, one thing we want to notice is that my lower bounds, I have two different lower bounds. My upper bound is constant, right? But my lower bounds would change. And so I'd have to break this into two double integrals, which we don't want to do. So when we set it up, we're going to be setting it up using left and right, okay? So instead of dy dx, we will use dx dy. So let's look at our setup here for these. My first thing I would maybe need to find would be the mass. And the mass is that double integral across R of the density. And like I said, we're going to use dx dy. So my setup for mass is going to be that y is going from 0 to 1, 0 to 1. And then my x values, we have x equals negative y and x equals positive y. And then I have my delta. So delta is a function. We have 3x squared plus 1. Oops, plus 1. I got to write it correctly. Dx dy. So with some fairly short calculations, we get that our mass is 3 over 2 or 1.5 kilograms. All right, let's look at the moment about the x-axis. So m sub x, my bounds would be the same. We'll say 0 to 1, negative y to y. But my formula, moment about the x-axis, is going to have delta y. So here, I will have 3x squared plus 1 y, dx dy. Integrating that, we're going to get 16 over 15 kilogram meters. My moment about the y-axis, following the same practice, but we'll have 3x squared plus 1 times x, dx dy. The moment about the y-axis simplifies to 0 kilogram meters. All right, so the only difference between mass and these two moments is the moment about the x has this additional y, and the moment about the y has this additional x. We would distribute, integrate, treating y as a constant up here. You guys have got this. You've been doing this over and over again. But now that we have these values, we can say that x bar is going to be m sub y 0 over my mass 3/2, which gives us 0. And y bar is going to be 16/15 over 3/2, which simplifies to 32 over 45. So my Center of mass, or my centroid, is going to be 0, 32/45. Moving on to the two moments of inertia, my I sub x formula is going to be both of those integrals cross r, y squared delta dA. And I sub y would look very similar. The double integral across r, x squared delta dA. So we already determined how we were going to set up our bounds. None of that is going to change. My I sub x, that's going to go from 0 to 1, negative x to x. We have y squared, and then we plug in 3x squared plus 1. We're going to integrate dx dy. That gives me 5/6 kilogram meters squared. And I sub y, same bound, 0 to 1, negative x to x, but we'll have x squared, 3x squared plus 1, dx dy. And that gives me 11/30 kilogram meters squared. And the last piece that we haven't talked about, that polar moment, it was defined in our table earlier, but the polar moment, I sub O, is going to equal I sub x plus I sub y. So in this situation, it is 5/6 plus 11/30, or 6/5 kilogram meters squared. All right, so good luck with all that integrating. Of course, the main thing we want to make sure that we can do is get it set up, because obviously in a real world situation, and especially if we're in class, we'd probably be using Maple or Wolfram to help us solve these integrals much faster. The main thing is knowing how to set it up. As always, email me if you have any questions. Good luck and good night.